Swayam Prabha. Digital India. Educated India.
Welcome back to the NPTEL course on muffler acoustics. This is week 4, lecture 2. Well, the contents for today's lecture, this lecture 2 is transmission loss TL and level difference LD, the development of expressions to evaluate transmission loss and level difference for a general muffler system. To facilitate our discussions for the transmission loss, I would like to go to the presentation, just a schematic here where you show the figure here. So, what do we see here? Well, we see a wave that is coming towards the muffler, directed towards the muffler, or quote unquote incident on the muffler, which is AN, and the wave front that propagates in the opposite direction, that is basically reflected from the muffler back into the engine system, which is your Bn. Now, this is the point n minus 1, this is 1, and this is your muffler proper. This is called the muffler proper, which can be, well, symbolically it could have any number of elements which are sequentially connected, something like this. You can have inlet, extended inlet and outlet, something like this, and you can have perforates as well. And you can have any short chambers, or point is sequentially connected, that is there is a unique or a uniform or a single direction in which the acoustic power propagates from the one end of the engine to the other end where the atmosphere is there. Anyways, what I am going to do now is basically develop the generalized expression for the transmission loss. So, when a wave is incident on the muffler, some part of course is reflected back, and then transmission loss is defined. It is independent of the source parameters, that is the source characteristics and the impedance. What is transmission loss? As the name suggests, it is the acoustic power. It is defined as the ratio of the acoustic power that is carried by the wave fronts that are incident on the muffler to the acoustic power that is transmitted into the anechoic termination. Now, here lies the crucial difference between the transmission loss and insertion loss. So, in insertion loss, the tube, the outlet pipe was simply exposed to the atmosphere. So, the radiation impedance was in play. Right now, by anechoic termination, it is a special kind of a termination, as we are seeing, as we discussed in our probably the very first lectures of the course. What we saw, that there is a wave, this A1 wave, it continues to travel infinitely along this direction. There is no reflection that goes on here, there is no reflection. So, why is this happening? Because you see this special kind of a arrangement or a device that is fitted. So, this is more like I do not have much space here, but imagine it to be the cross section view, something like this, and the annular part is filled with some sound absorbing or a dissipative material. So, and of course, basically what is happening here is that you have your a conical pipe, which is more like a frustum of a cone, and it extends for a sufficiently large distance, and is filled, the annular material here is filled with dissipative or sound absorbing material, and they are backed by a perforated tube. So, basically as the waves acoustic energy, acoustic power traverses in this uniform pipe, it gets a chance to interact or escape through the holes to the annular cavity, where the acoustic power is completely dissipated. So, the larger the length, the more will be the attenuation as it goes at this end, and at some end of course it has to meet the atmosphere. So, but the trick here is that to make it of sufficiently large length, so that by the time the acoustic power reaches here, most of it is dissipated and there is nothing left to be reflected. It is sufficiently dampened, or the amplitude has died down a lot. So, this anechoic termination, basically it is a kind of a conical arrangement, frustum of a cone arrangement filled with the annulus of which is filled with dissipative material with the aim to absorb sound, and so that there is no reflections by the time the wave reaches the other end. So, its job then is to prevent the waves B1 that would have propagated or reflected back into the muffler from the open end, as was the case when the termination was exposed to the atmosphere. So, this anechoic termination serves the purpose of allowing only a unidirectional or one this direction propagation of waves and not allowing the waves to come inside. But on the upstream, so this is the downstream part, downstream thing. This is the upstream. So, basically the idea is to ensure that whatever waves are incident, some part was reflected back, and that is crucial. If nothing is reflected back and everything is propagating downstream, then the muffler is useless, because it is not doing its job properly. On the other hand, if B is nearly the same as A and A1 is tending to 0 in such an arrangement, then muffler is very effective at that frequency, it is doing its job very well. So, and obviously in the first case that I discussed, where A1 is nearly the same as AN, then of course transmission loss will tend to 0. The muffler is acoustically transparent or useless. We'll see how we got to this stage. We will now make use of our this expression for transmission loss. So, this is our friend, we will use it. So, let me write down this thing, TL is half rho times real part of pressure times V, this thing, V tilde mass velocity complex conjugate. Now, what is P tilde? For a tube, it is AN e to the power j k naught x plus Bn So, as we have been discussing a lot, forward propagating wave, backward propagating wave. Now, we are interested in finding out the acoustic power that is transmitted by this wave. So, what is that? We put this here, AN e to the power minus j k naught x, and what is, we will just consider this circle term, and what is the mass velocity? Let us first derive it. So, mass velocity from Euler equation, if we do it, we are going to get rho naught j omega u is equal to, take a spatial derivative of this, AN times minus j k naught x. Okay. So, j will get cancelled, and this is omega by C, omega gets cancelled, and this is C naught actually. So, what we are going to get, u is nothing but 1 by rho naught C naught, and this is what we are going to get. All right. So, when you take the complex conjugate of this, so this will become plus, and this is A star. So, when we write down this thing, it will become, probably let me use the green color itself, AN complex conjugate times e to the power j k naught x, and remember we have the mass velocity here. Also have to do is that multiply this thing by rho naught and multiply further by S, so the cross sectional area. So, we get S here. So, this would mean this is nothing but V tilde star is equal to this. So, this was nothing but Y naught. Remember, Y naught, the characteristic impedance of a duct is C naught by S, cross sectional area. So, here in the denominator we are going to get this. So, this will cancel, and what are we left with? We are left with acoustic power that is incident is 1 by 2 rho naught times Y naught A mod A square, because A mod A square is A into A this thing incident. So, similarly the power that is reflected, it can be easily shown that it is nothing but this thing. Okay. Now, couple of things here. If we were to directly plug on the expression for P and derive the complex, well, a little bit formidable expression for particle velocity and get the mass velocity expression where it has both the terms A and B, then we do all this business of half of rho naught times P into V star complex conjugate. So, what we probably would get something like this, the same expressions like these ones, but we will get something like this thing, the power that is carried away by the forward propagating wave and the acoustic power that is reflected back. And by doing some algebra complex analysis, the cross terms will cancel out. Well, so this is just to verify our computations. Similarly, I mean, if you let me just go back to the presentation, and we see here the wave that goes here, the acoustic power is nothing but A1 square mod A1 square by 2 rho naught y naught. So, here of course, the duct area assumed to be constant, they need not be, but what we can do now is get back here and write down the expression for power transmitted in the downstream, which is this is let me write this A n, this is B n, this is A1 mod A1 square, remember, and this can be your y n, this is this thing, y1, all right. Remember, B1 is 0, so no power is transmitted back upstream. So, by the definition of transmission loss, let me write it in big fonts, because that is what we are going to use for a large part of our course to evaluate the performance of a muffler. I am going to talk about that shortly. It is defined as acoustic power incident divided by acoustic power transmitted. So, it is pretty simple to then figure out that this then becomes rho naught gets cancelled, and what we are essentially left with is A n by A1 mod square, and in the numerator you will probably have so this is y n, right. So, here you will get y1 and y n, and once you simplify you will get S is a cross section area, S n by S1. So, generally we often have the thing that the inlet and outlet pipes are the same. So, y n is equal to y 1 because the cross section area of the inlet upstream pipe is the same as the downstream pipe. In such a case, T L reduces to the following expression: T L is equal to 20 times log to the base 10 A n by A 1. So, this is as simple as that. Transmission loss then is the 20 times the logarithm of the incident wave amplitude, ratio of the incident wave amplitude to the amplitude of the wave that is transmitted downstream into the anechoic termination. So, computationally there is no difficulty, in the sense that if we were to do a proper analysis of this muffler part by some 3D consideration, 1D considerations, or numerical 3D schemes, or even experimentally is a different story. I am going to talk about that briefly, but if we were to do it analytically or numerically, then transmission loss is perhaps the easiest to evaluate. Insertion loss is the most difficult. This is what it is. Now, couple of things here. So, is there any limiting condition under which transmission loss and insertion loss are related? Well, it turns out that, well, in the limit where P1 is equal to the pressure in the downstream port where you have anechoic termination, P1 becomes A1, because B1 is 0 like I have mentioned. This thing then becomes y1 times mass velocity V1, and your Z naught is y1, that is the atmospheric impedance is the characteristic impedance of the tube. This is a very important condition, and the upstream part, that is the upstream wave that is incident, is given by simply P n by y n into V n by 2 divided by 2, y n because the source impedance has been replaced by this y n thing. So, then what happens is that the equation that we just derived now here, let me call it star, T L would become in the limiting case 20 log base 10 P n plus y n times V n divided by 2 times y 1 into V 1 using this relation. This is simple to see. How do we get it? So, basically what we will get is this is the base thing, and with z naught equal to y 1. So, as the progressive wave does not undergo a change in the amplitude while moving across a uniform tube, A n and A 1 can be measured anywhere in the respective pipes. So, basically this thing can also be written as 20 times log of P n plus y n V n minus 1 divided by 2 y 1 V 1. So, z naught is of course given by this thing. So, we will see that transmission loss then is the limiting case or the general case of insertion loss when the atmospheric impedance is replaced by your anechoic termination. So, now the thing is, like I was mentioning, transmission loss is probably the easiest to compute of the 3 parameters IL, LD and TL, but experimentally it probably is the most difficult to do. Why? Because of the necessity of anechoic termination. Before even we begin to attempt the measurement of transmission loss, it is a good idea to talk about the development of a suitable anechoic termination facility, that is basically a tube with which would attenuate wave. So, it has to be filled with like I said, rock wool, glass wool, some dissipative stuff, and its reflection coefficient needs to be checked, absorptivity should be high for a given length. So, then we can use that anechoic termination and use certain experimental techniques to figure out the acoustic waves that is transmitted downstream. But suppose even if we do not have anechoic termination, it is still possible to measure transmission loss, but it will require the development of more complicated more advanced experimental techniques named as 2 source method or 2 load method. I am not going to discuss about that now just yet, but just sort of mentioning that TL is a little bit more difficult to measure experimentally. Okay, that is about the transmission loss, but one thing is there, TL really tells you how good or how bad a muffler is. Unlike insertion loss, transmission loss can never be negative. Why? Because it is really the ratio, for at least for a conservative system. There are no sources within a muffler's chamber, then transmission loss is always positive. In the worst case or in the minimum thing, TL can be 0. Now, this is something that I did not discuss, I should have. This, when this quantity is equal to 1, that is A n is equal to A n, so the TL then becomes or tends to 0, that is the muffler is transparent as I was briefly mentioning, and for a large A n by A 1 value, TL is high, that means very good performance. Now, the thing is, transmission loss is probably one parameter that is completely independent of the source characteristics PS and ZS. So, if you have a certain source and if you want to design a muffler without worrying much about the source characteristics, and you want to compare 2 or 3 or more different muffler sets, which one is the best suited as far as noise attenuation is concerned. So, one can actually evaluate, develop some computational schemes or analytical schemes to calculate the transmission loss performance and compare across different models, different configurations. So, that would give us a good idea of the sound reflecting capability of a given muffler or a sound absorbing capability. In summary, the noise attenuation capacity of a muffler without worrying much about the source characteristics. Now, finally, we come to the another part of the talk, level difference. So, level difference or the noise reduction is also known as noise reduction. That is probably the most, perhaps the simplest to experimentally evaluate. It basically is the difference in the sound pressure levels at 2 arbitrarily selected points. So, if we have again a complex muffler element, and if we were to take a microphone and measure the pressure inside the duct at certain point and certain point here. So, the basically just LD, the logarithmic difference, LD is equal to 20 times log to the base 10 of P n by P 1, this thing, that would give us the level difference. So, unlike transmission loss, the definition of level difference does not make use of standing wave pressures and does not require a anechoic termination. And for the purpose of calculations, however, P1 may not be known directly. So, we can develop some suitable relationships and evaluate this P1 in terms of the acoustic pressure somewhere measured right here. So, it turns out that after some algebra, a level difference then may be expressed in the terms of 20 log, obviously I am not writing 10 here, it is base 10, P n, ratio of the pressure measured upstream of the muffler to the pressure measured right at the downstream, divide by cos k naught L L1 plus j y1 by z naught, that is the atmospheric impedance, times sine of k naught L L1. So, and if L1 is tending to 0, that is, or probably I should mention this as L1 dash, I am sorry. If L1 dash is tending to 0, then level difference will be just 20 log P n by P naught. So, then level difference is a limiting for a constant pressure source, as we discussed, constant source, that is your Ps is tending to 0, level difference and insertion loss are the same. So, level difference is a limiting value of insertion loss for a constant pressure source. So, level difference, like I was mentioning, it does not require the source impedance and source characteristics, basically acoustic source pressure and source impedance, and also does not require anechoic termination. So, therefore, it is easiest to measure and also calculate, perhaps, that is using maybe FE codes and analytical things, and it has become a very popular measure to do some experimental corroboration. But what really matters? What really matters is the ability of a muffler. It is neither transmission loss nor LD. Those are good for LD. Transmission loss is good for basically, let me just summarize this in the table for the benefit of the students here in this course, that tabulated comparison of the pros and cons of TL, IL, LD. Experimental, difficult, well, relatively easy, very easy, analytically or prediction wise, much easier. By prediction, I mean using analytical thing or numerical, analytical or numerical, because it does not involve source characteristics. Tough, because it requires source characteristics, which is not a easy thing to do by any means, easy. Now, what is the physical significance? Physical significance, we can compare, we can get a good idea of a given configuration without even bothering whether what happens when the muffler is put in actual operating conditions. So, we can compare different mufflers. This is what matters the most, insertion loss. Some matters most. It's something like, to put it very bluntly or grossly, you would, if you pay to an acoustic consultant, lakhs of rupees or millions of dollars, whatever it is, that your ultimate objective is to basically tell us that whether the muffler or the noise control measure is good or not. You would eventually want that without the muffler, whatever the noise is there, it should really come down when the muffler or the noise control measure is put in its place. So, the idea is that insertion losses, like I said, like I have been mentioning, simply put, if you remove that thing, the noise is too large. If you put that thing on, the noise is too less. So, it works, you are happy. So, that is what matters the most, without even bothering about complicated things like anechoic termination or not. It is just your atmosphere is there. So, whatever impedance it imposes, it does. So, experimentally it is easy to do, and that is what matters the most. computationally the toughest part to evaluate. Level difference, well, is the easiest to measure experimentally, well that is what I have written, and can give us a good idea of the effectiveness of a muffler system. At the end of the day, insertion loss should be good, then you have done a good job. So, I guess with this background we can just stop for the day, and we will probably resume in the next class where we talk about performance of different muffler configurations, where simple constituent elements like a sudden area expansion and extended inlet and outlet things, and simple expansion chamber of course, and the similar things. So, that will be very interesting to see what happens when you just consider a plane wave analysis and go about evaluating the performance of such mufflers. The idea is obviously the plane wave, like I said, it is too simple or it will break down, but it can give us a very good feel of the system. So, that is what our aim should be, and we are going to talk about that in the next few lectures. Probably the next few lectures are going to be devoted to a range of elements that constitute simple elements that constitute a muffler, and I will show some sketches and talk about the basic philosophy, how mufflers operate. With this, I guess I will stop here. Stay tuned. Thanks a lot.